All right, so we're going to do a little extra practice on potential energy and kinetic energy problems. So we'll start out here. I'll do a couple examples from potential energy, and then I'll move on to kinetic energy. And I want to remind us, just before we start here, that potential energy is going to have the following formula. So our potential energy here is going to be PE for potential energy is equal to the mass of the object. Now remember, the mass needs to be in kilograms, and then you multiply that by G for gravity, and then you multiply that by the height in meters. Okay, so those are the variables that we will be utilizing. So I'm going to do problems number 1 and number 2 here, and then I'm going to leave you to do problem 3. So it says a science student holds a 55-gram egg out of a window. Just before the student releases the egg has 8.0 joules of gravitational potential energy with respect to the ground. We want to know how high is the student's arm above the ground in meters. And I give you a little hint here. And I'm just going to remind you one more time that the mass needs to be in kilograms. Okay, so we're just going to list out our variables here. So we have our potential energy, our M for mass, and over here I'm going to put our G for gravity and our H for height. Okay, so our potential energy. Remember, energy in this case or this instance is going to be discussed in terms of the unit joules. So if you look through the problem, the value that it gives for the energy is 8.0. So our potential energy is 8.0 joules. And then our mass is given at 55 grams with that egg, but remember, this needs to get converted to kilograms. So just as a reminder, you could plug that into Google, but just as a reminder, we take 55 divided by 1,000, and this becomes our mass in kilograms. So 55 grams is equal to 0.055 kilograms. Okay, that's really important as we go through this problem. Now, the gravity is always going to be the acceleration due to gravity unless otherwise stated. Now, our acceleration due to gravity, we're on Earth. We don't live on another planet quite yet. So on Earth, the acceleration due to gravity for our potential energy problems is going to be 9.8 meters per second squared. Again, that is almost a constant unless I say we're on another planet. Always use 9.8 meters per second squared unless told otherwise. And then ultimately here, if you remember the question, it said, hey, how high was this person's arm? So our height is our question mark. So now what we need to do is just plug everything back into our formula. So our potential energy of 8.0 joules is equal to our mass in kilograms, which we just said, or we just solved for, at 0.055 kilograms, times our acceleration due to gravity, which I told you, unless otherwise stated, it's always going to be 9.8 meters per second squared. So we have 9.8 meters per second squared times our H for height in meters. Now, to get all of this by itself and solve for H, we divide everything attached to 8, okay? Or excuse me, everything attached to H. So we divide by 0.055 kilograms times 9.8 meters per second squared. And then what you do to one side, you have to do to the other. So 8 is going to get divided by 0.055 kilograms times 9.8 meters per second squared. Okay, I know it's kind of squished here, but the way in which we're going to solve this problem is as follows. We're going to take 8, so 8.0, divided by, very key thing here, parentheses, 0.055 times 9.8. Close the set of parentheses, and we get our height. Now, we're going to round this to the nearest whole number, and so the nearest whole number would be 15. So our h is 15 meters, and that is exactly what the problem wanted. Okay. Now, we're going to go through this next example here. A diver has 3,400 joules of gravitational potential energy after climbing up onto a diving platform that is 6 meters above the water. We want to know, what is the diver's mass in kilograms? So again, we start out. Our potential energy, remember, is the item or is the variable given in joules. So look here, the problem gives us 3,400 joules as our potential energy. We go down to our M for mass. Well, if you look here, it says, hey, what is the mass of that diver in kilograms? So that becomes our question mark. And then we move over to our gravity. Again, unless I tell you we're on a different planet, or unless I tell you otherwise, G for gravity is going to be 9.8 meters per second squared. And then our H for height. That is how high that diver is above that water. It tells us that the diver is 6.0 meters above the water. Okay, so we just plug all of this back into our equation. So we have 3,400 joules equal to our mass, which we don't know. So we're going to call that M, times our acceleration due to gravity, 9.8 meters per second squared, times 6.0 meters. Now, to get M by itself, we need to divide by everything it's attached by. So we're going to divide this side over here by 9.8 meters per second squared times 6.0 meters. We then do the same thing on the other side. So we're going to divide 3,400 divided by 9.8 meters per second squared times 6.0 meters. Okay, so what we're going to do in our calculator is we're going to take 3,400 divided by 9.8 times 6. So 3,400. Plug that into our calculator. Divided by 9.8 times the height of 6 meters. You close that parenthesis, you press enter. All right, so rounding to another whole digit here. This is going to round to a mass of 58 kilograms. So our mass here equals 58 kilograms. Okay. All right, so I want you to do number 3 on your own. We're going to move down here to our kinetic energy problems. Now remember, kinetic energy has the formula of Ke for kinetic energy equals half times the mass times the velocity squared. Okay, and the velocity squared is very key here. So I am going to do problems number 4 and number 6, and then I want you to do problems 5 and 7. So problem number 4 reads as follows. Calculate the kinetic energy in joules of a 1,500 kilogram car that is moving at a speed of 42 kilometers per hour. Now, look here, it gives us a hint. We need to convert the speed to meters per second before we go into this equation. So, again, let's list out our variables here. Our kinetic energy, Ke, is again in joules, and if we look closely, we don't see a unit in joules, so this is going to be our question mark. Now, our M is for the mass of whatever object we're looking for, and the mass of this object is 1,500 kilograms. So 1,500 kilograms. And then we have this. We have a speed or a velocity of 42 kilometers per hour. Now that's not very useful because we need it in meters per second, okay? So what we need to do, and I don't expect you can look this up online, but what we need to do to convert this to meters per second is the first thing, we need to get to units of meters, so we'll multiply by 1,000 meters. And then we need to cancel out that unit of hours on top. And for every 1 hour, there is 3,600 seconds. Okay? So what I'm going to do in my calculator is I'm going to take 42 times 1,000. And then I'm going to divide that answer by 3,600. And I get a value. I'm going to use 11.7 meters per second. So our velocity equals 11.7 meters per second. Okay. Now, I have my unit of meters per second. I am going to plug that along with my mass into my kinetic energy formula. So here, our kinetic energy is equal to the mass in kilograms, so 1,500 kilograms, times our velocity that is squared. So 11.7 meters per second, and this needs to get squared. Okay, so what I do in my calculator, and this is really important here, I take 1,500 or 1,500 times, put a set of parentheses, make your life easy there, and then I'm going to square 11.7. So I'm going to multiply by 11.7 squared, and I press enter. So our value here for, big mistake here, big mistake. I forgot a key part of the formula. Okay, this is key. I thought the answer looked kind of goofy, and this is why. So our kinetic energy, don't make the same mistake I did, is half times the business that we just multiplied it. So half, remember, 1 over 2 is half, times the mass in kilograms, times the velocity squared. Okay? I press enter. That looks a lot better. So in my calculators, you could leave it like this. I'm going to round to the next whole number. So it's going to be 102,668 joules. So again, kinetic energy for this particular problem is 102,668 joules. All right. Now, again, key thing here, do not forget that half like I did, because that will make a difference in your answer. Okay, moving on to number 6. So number 6, it says the largest land predator is the male polar bear, which typically has a mass of around 5.00 times 10 to the second kilograms. If the maximum kinetic energy for a polar bear with the mass stated above is 6.05 times 10 to the fourth joules, we want to know how fast can it move, or what's its top speed. So our kinetic energy, we start with this, is given at 6.05 times 10 to the fourth, 6.05 times 10 to the fourth joules. So 6.05 times 10 to the fifth, how about 10 to the fourth? There we go, 10 to the fourth joules. Now the mass of the polar bear is equal to 5.00 times 10 to the second kilograms. So the mass of the polar bear is 5.00 times 10 to the second kilograms. All right. And then our velocity is something that we don't know. So let's plug all this stuff back into the equation. So we have 6.05 times 10 to the fourth joules equal 5.00 times 10 to the second kilograms, and this is really important, times our velocity squared. Whoop, and I did it again. I need to put that half. So it's really important that we put that half there because that is part of the formula, all right? So, again, don't do as I first did in these problems here, but we need to put the half because that is part of the kinetic energy formula. So we get half times 5.00 times 10 to the second kilograms times our velocity squared. Okay? So we need to get v squared by itself. That's our first step here. So we're going to take half times 500 times, or excuse me, 5.00 times 10 to the second kilograms. And we're going to divide it on both sides. So we'll have half times 5.00 times 10 to the second kilograms. Okay? So in our calculators, there's going to be a lot of parentheses here. So we're going to take 6.05 times 10 to the fourth. That's our maximum amount of energy here. We're going to divide that by, put two sets of parentheses, so you have half. Then you multiply that half by the polar bear's mass, which is, again, other parentheses, 5.00 times 10 to the second. You need to put two sets of parentheses here, and you get 242. Now, we're not quite done. We're not quite done because this is 242 meters squared per second squared equals our velocity squared. Now, remember from math class that to get a squared by itself, so to get rid of the squared power, you need to take the square root of both sides. So what we're going to do in our calculators is we are going to take the square root, the square root button. We're going to put 242 inside the set of parentheses, and that velocity, we're going to round to one decimal here, is 15.6 meters per second. So 15.6 meters per second equals our V for velocity. All right, so a key thing here with kinetic energy, don't be like me, don't forget about this half. That half is very, very important to remember as you do these other problems. Again, I need you to do problems 3, 5, and 7 to complete this particular assignment.